Hi everyone, and welcome to the solutions for the physics topic test on module 5. Let's get started with the multiple choice. So for question 1, we have a projectile motion, and which arrow represents the acceleration of the projectile at its maximum height? Well, we know in projectile motion, the acceleration is always constant. That's just gravity acting straight down, and so the answer is C. Question 2 says, which one of the following is true for all objects undergoing uniform circular motion? Now, A is wrong because the direction of the velocity is always changing, and so it's not constant. And we also know that C is wrong because the acceleration is always changing, it's always towards the center. B is also wrong because in some instances of uniform circular motion, the total energy could be other types of energy such as gravitational potential energy or nuclear or heat energy, and so that's not always true. But what is always true is that the object experiences a constant magnitude of net force, and this is in fact the centripetal force. Okay, question 3 says, an object travels in uniform circular motion at a speed of 4.5 meters per second around a circle of radius 6 meters. Which of the following is the frequency of rotation of the object? So to find the frequency, we can take 1 over the period, or in other words, we just get 4.5 divided by 2 pi times 6, and we should get the frequency is 1.2 times 10 to the minus 1 hertz, so the answer is A. Question 4 is asking us on torque, and we have a variety of distances from the bolt here. We have a variety of angles, and we also have a variety of forces. And so all we need to do is just calculate the final torque, and actually these should be Newton meters. We calculate the final torque for each of the options using the formula that torque equals to Rf sine theta. And we find that the maximum torque is given by F3, so the answer is C. Question 5 says, the projectile is launched as so, and it's going to land on the ground at B. And which of the following can be applied to the projectile such that the projectile would still land at point B when launched from point A? Now the key word here is changing only one of these variables only. If we change only the launch height, the projectile would land somewhere here. If we change the launch speed, it would also land somewhere here. If we change the launch angle, if we change it up, it might follow a projectile as such, or a trajectory as such. If we only change just any one of those factors, that's not going to allow us to keep the same range, the same exact range B. We have to change one or more. For example, we could decrease the launch angle, but also increase the launch velocity. That will help us B. Or we could follow a trajectory like this, in which case we would be increasing the launch velocity and also increasing the launch angle. Okay, so it's not possible only changing one of the variables, and so the answer is D. Okay, question 6 is asking us about the energy and the orbital period of low Earth satellites and geostationary satellites. Okay, and it's important to note that say if this is the Earth, then the low Earth, LEO, would be orbiting somewhere around here, and the GEO would be in a high orbit somewhere around here. So knowing that, we know that since the GEO has a larger radius of orbit, its orbital period is also going to be larger, right? Because it has to travel, this further distance here. As for the total energy, we know that the further you get away from a mass, your gravitational potential energy increases since U equals to minus Gm m on R. That's a minus sign, so the further away you are from the mass, the more your energy increases. And so GEO will also have the greater total energy, and so the correct answer is D. Question 7 is to do with Kepler's third law. So we have a dwarf planet with a period of 40,000 years around the Sun. The average distance from the Sun to the Earth is 1 astronomical unit. What is the average distance between this dwarf planet and the Sun in astronomical units? Essentially, we know from Kepler's third law that the ratio r cubed on t squared is going to be a constant for all objects orbiting the same celestial body. In this case, the celestial body is going to be the sun. So r1 cubed on t1 squared equals r2 cubed on t2 squared, where r1 is going to be 1 is going to be a dwarf planet, 2 is going to be the Earth. So we can rearrange this equation to solve for r1, and we get that r1 is equal to r2 times the ratio of the periods t1 and t2 to the 2/3 power. Now the ratio of their periods, well, t1 is equal to 40,000 years, and t2 is equal to just 1 year, because the Earth takes 1 year to go around the sun, and so that ratio is 40,000. Raise that to the 2/3 power, and you should get C, 1,170. Alright, the next question is asking us about orbital velocity. So, if we increase the distance of orbit, if we increase r to 2r, if we double it right here, what's going to happen to the orbital velocity? Well, since v is proportional to 1 over root r, if we double r, then v is going to decrease by 1 over the square root of 2, which comes out to approximately 0.7. And so the answer is B. Alright, question 9 is another multiple choice where we have to go through all of the responses and pick the best one. Okay, so for this question, let's go through each of the responses. So the first one says the sum of the forces on the cube is 0. That's not going to be true, because after the string is cut, where the cube is most likely just going to, fall down, or it's going to accelerate in some direction. It's going to move, basically, and so we know the sum of the forces can't be 0, so that's wrong. Let's look at option B. Option B says the horizontal force of the blackboard on the cube is equal in magnitude to the horizontal force of the cube on the blackboard. Now this is really just Newton's third law, right? That the force of A on B equals minus the force of B on A, and since we're talking about magnitude, the forces are going to be equal. And Newton's third law is applicable to pretty much every scenario. It's a universal law, and so B has to be correct because it's simply a restatement of Newton's third law. And so we can just stop at option B. Alright, question 10, another tricky mechanics question. And let's go through the options here, okay? So it says that the ball follows a trajectory around the roll between landing on the ground opposite its starting point, does not reach the top of the wall, assume that there is no friction between the ball and the wall, which statement correctly describes the net force acting on the ball during its motion. Now we have sort of two kinds of motion going on here. First, of course, we have projectile motion, and that's because the ball is being projected, alright? And so there's a constant force of gravity. But we also have circular motion going on, right? And in circular motion, there's a constant centripetal force that's always acting towards the center. And so even if we combine these two types of motion, the net force, since the net force in projectile motion is gravity, that's constant, in circular motion, the net force is the centripetal force, that's also going to be constant. And so if we add those two forces together, the magnitude of the net force is going to still remain constant. And so the answer is A. Alright, down to some calculation questions here. So, question 11, we're dealing with concepts of mass and weight. All you need to do is figure out the mass of the object on the Earth, and then multiply that by the field strength of Neptune. Pretty straightforward, and you should get the answer C. Question 12, we have a projectile launched from the ground, range of 60 meters, in the air for 4 seconds, calculate the angle. So we know that the projectile reaches its max height at a time of 2 seconds, which is half of the total range, right? Assuming that the flight path is going to be symmetric here. And so we can use our equation in here. I should use the equation that Vy equals to Uy plus At, right? But since at the max height, V is going to be 0, so we simply get that Uy equals to gt, where g is the acceleration, right? And so this 19.6 comes from essentially 2 times 9.8. Right. After that, we know that the distance that it travels, the horizontal distance that it has traveled when it reaches the max height, is going to be 30 meters, which is also half of the range of 60 meters. Again, we're assuming that the flight path is going to be symmetric. And so the initial velocity in the horizontal direction, well, that's just given by the formula. This comes from that change in x equals to ux times t. We rearrange that and you get ux equals to the distance 30 divided by 2, the time, and we get 15 meters per second. And so finally, we just need to take the inverse tan of the ratio of the vertical velocity to the horizontal velocity to get the launch angle, which is 53 degrees. So the answer is C. Okay, the next one is another question on Kepler's third law. And it's asking us to recall which of the following variables affects the value of k. Now, we know that Kepler's third law is that r cubed over t squared equals to gm over 4 pi squared. Now notice that m, this is the object that other objects are orbiting around. Okay, so this capital M, this is the object that is in the center of all the orbits. It's the one that's creating the orbit. And so in this scenario, what's the thing that everything else is revolving around? Well, it says everything is revolving around the star. And so the mass of the star indeed affects the value of k. Okay. Cool. Question 14 says, a ball was thrown upward at an angle of 45 degrees. It landed at the same height as thrown. Which graph best represents the kinetic energy of the ball during its time of flight? Now, you have to notice that as the ball, so the flight path of the ball will be something like this, right? Now, as the ball goes up, as it is launched higher and higher into the air, its kinetic energy will actually decrease, right? And it's decreasing because its vertical velocity is decreasing due to the acceleration of gravity downwards. And so it'll start off with some amount of kinetic energy, then it's going to decrease to a minimum when it reaches its peak there, because at that point it only has its x velocity left. And then it's going to increase again as it speeds up on its way back down to the ground. And so A is not going to be correct because the kinetic energy is not going to increase. D is also incorrect because it's not going to decrease forever. It will gain some more kinetic energy as it speeds up towards the ground. And C is also not correct either because it's never going to hit this 0 point here because it still has some velocity in the x direction at its peak. And so the only correct answer is going to be B. Question 15 says, we have a Ferris wheel and there's essentially two different torques acting on it. We have the torque from this carriage A, and that's providing a torque in obviously this direction. And we also have a torque from carriage D, which is at an angle of actually 45 degrees to the axis of rotation, right? And it's 45 degrees because there's 8 evenly spaced Ferris wheels, so that means that 360 degrees divided by 8 equals 45 degrees. So it's at an angle of 45 degrees to the axis of rotation. And so it's applying a torque in the opposite direction. And so the magnitude of torque coming from the two barrels on the Ferris wheel is going to be the torque from A, which is simply going to be 100 times G times R. And we're going to minus 100 times G times R times sine of 45 degrees, which is 1 on root 2. And if you work that out, you should get A, 5,741 Newton meters. Alright, question 16 is another multiple choice question. And it says that we have a bus that's moving in this velocity here, and the string holding the mass is cut. At the same instant, the bus driver applied the brakes, causing the bus to slow down at a rate of 3 meters per second squared. So there's going to be a net force acting in this direction. So which statement correctly describes the resulting motion of the mass observed from within the frame of reference of the moving bus? Now, within the frame of reference of the moving bus, there's still going to be a net force that's acting towards the end of the bus, right? However, due to the inertia of the the inertia of the mass here, and when the bus suddenly slows down, it's going to want to keep moving in this direction. It has inertia in this direction. Okay, so the mass is going to want to keep moving in the direction of the bus. And so when the string is cut and the bus slows down, it's going to follow a path like so, because its inertia is going to carry it moving that way, and then also gravity will pull it down. So it's going to follow that sort of path there. And so the correct answer should be D. Travels in a parabolic path downwards and towards the front of the bus. Alright. Question 17 is again dealing with projectile motion. This time it's in a lift, okay? We have this projectile motion scenario, and that's when the lift is stationary, and that's the path that the projectile follows. The projectile was again launched with the same velocity, but the lift is now slowing down as it approaches the top floor, which diagram correctly shows the new path of the projectile, relative to the path created in the stationary lift, which is the solid line. And so the question here is, what sort of dotted line will the projectile make? Now, if you think about it clearly, if the lift is slowing down, that means from the outside of the lift, there's going to be a net force on the lift there's going to be a net force as seen from the outside. But from the inside of the lift, the apparent weight of the ball is actually going to be lighter. And so it will follow this path as shown here. It's actually going to travel at a higher height than the trajectory that it took when it was stationary, and so the answer is going to be C. Okay, question 18 is a graphical representation question, and we want to essentially find the relationship between the time that it takes for a projectile to fall to the ground and the height from which it was dropped from. Now, according to the Subat equations, we have that S equals to half AT squared, and I've omitted the UT term because it's dropped from rest. The ball was dropped from rest, right? We're going to assume that, and so UT is going to be equal to 0. And so if we rearrange this equation to solve for the dependent variable here, which is time, we get that t equals to some constant, which is all this half a business, times the square root of s. And option A clearly shows a square root relationship between time and height, and so the answer is A. Question 19 is again dealing with projectile motion, and here we have that we have two shots by a batsman. Both balls reach the same maximum height, but ball Q travels twice as far as ball P. Which of the following is different for balls P and Q? Well, we can immediately discount option C and D because the gravitational force and acceleration is going to be the same for all projectiles on Earth. So now it's between A, time of flight, or B, initial velocity. Now, it is possible it is possible for the time of flight to be the same, right? Because if ball Q is traveling faster, that means it will also reach the ground faster. And so the only possible answer here is that the initial velocity is greater, and that initial velocity is required for it to get that max range, right? Because the range is given by uxt, and so a higher initial velocity will get a higher range. Alright, last question, and that we have is question 20. So a passenger is playing billiards on a train that is traveling forwards on a level track. The ball takes the path shown when hit by the cue. So you would expect the ball to move straight, but because the train is in fact moving, it's going to curve in this direction over here, and that's because there is some sort of force that the train is acting on the ball, right? And from an outside perspective, that's going to be a net force in this direction, right? But as before, if we are inside the train, we can consider the inertia of the ball, right? So the inertia of the ball wants to keep moving in this direction. So why would it apparently curve in this direction? Well, it's because the train has either moved right or it's moved left, and so the inertia is going to carry it to one of the side positions shown, right? And so if you just imagine that the train turns left, right? If you just imagine that the train's going to turn left, then the view of the this diagram will become like this. This will now be the front of the train, right? We've just taken this front train and we've just turned the train left, and now the front is facing in this way. But the ball is still going to move, it still has inertia in this direction, right? And so it's going to keep moving in this same direction to the right here. And so the ball will actually hit this area. Now, if you reorient yourself, if we just rotate this diagram over here, so it matches this diagram over here, we're gonna see that, you know, this is the front, and the ball has hit this area of the train here, which is exactly what we see in this diagram, right? It goes to the bottom portion of the table here. And so we know that option A is actually correct, and we deduce that by considering the inertia of the ball. Okay, so now we'll move on to the short answers. So, question 21, we have another projectile motion question. A projectile is fired at 26 meters per second at an angle of 34 degrees and lands on the point T on this adjustable platform here. So, to find the initial and horizontal and vertical velocities, very straightforward. Just get 26 times cos 34 degrees, 26 sine 34 degrees, and you should get these values here. Justify whether the projectile will hit the ceiling of the tunnel. Well, we know the ceiling of the tunnel is 12 meters, so all we need to do is figure out the max height that the projectile will reach, and if it's less than 12 meters, then it will not hit the ceiling of the tunnel. Well, we know at the max height that the vertical velocity is equal to 0, and so we can use our Suvat equation. The equation I've used here is v squared equals to u squared plus 2as, or interchanging y here, right? And we already know the initial vertical velocity because we worked that out in the last question. And so we can rearrange this formula to get that the max height is going to be 11 meters, which is less than 12 meters, and so it will not hit the ceiling of the tunnel. 21C says, find the time of flight of the projectile. We can use our equation, S equals to ut plus half at squared. At the max height, when the projectile lands again on the ground, its vertical displacement, its delta y, is going to be 0, right? Because it has no vertical height, right? So we can substitute that in. 0 equals to uyt minus 4.9. Minus 4.9 is simply just half g. It's minus because gravity is going down, t squared. We can divide through by t since t is not equal to 0. And then we can rearrange to solve for t, and you should get that t is equal to 3 seconds. Then, to find the range r of the projectile, we simply need to use this formula, that the range is equal to the initial horizontal velocity times the time of flight, which we just worked out earlier, and you should get 64 meters per second. Part E says the adjustable platform is now raised from A to B, so it has been raised upwards like this. So now the projectile needs to land like this. So, explain how the cannon can be adjusted to hit point T on the platform. So, there are two ways to do this. We can either increase the launch angle, or we can increase the launch velocity. Both of these factors will increase the range of the projectile, and so instead of landing at this spot T, it will land maybe at this spot, you know, T prime, right? And so, it's going to take a path that is perhaps something like this. Alright, question 22. It says a roller coaster design has a section of turn which is banked at 80 degrees. Assume that friction is negligible. The carriage can take the turn at a maximum speed of 34 meters per second. Find the radius of the turn. Now here, we want to recall the formula we use when we are doing circular motion on banked turns, and that is the formula v squared equals rg tan theta. And we can actually prove this formula at the end of the topic test. As the formula, all we need to do is just rearrange to find the radius of the turn. That's v squared on g tan theta. Substitute all your values and you should get 21 meters. Alright. And it says that the maximum acceleration we can get safely is going to be 4g, 4 times the gravitational acceleration. And we want to find the maximum safe speed that the carriage can take the turn. Here it's even simpler. We just need to use our good old equation, a equals to v squared on r. That's the centripetal acceleration formula. Rearrange that for velocity, and you should get that velocity equal to square root of the maximum acceleration, which is 4g, times the radius of the curve, which is 21, and you should get 29 meters per second. Okay, 23 is another circular motion question, and this time we have a 7.8 kilogram mass attached to the end of a string, which is whirled in a horizontal circle of radius 4 meters as shown. The mass completes one cycle of motion in 5 seconds, and the string can withstand a maximum tension of 100 newtons before it will break. Okay, so we want to find the angular velocity of the mass. All we have to do is recall the formula for angular velocity, which is 2 pi on t, where t is the period, and that's because the angular velocity is just the angular displacement, which is 2 pi radians divided by the time it takes to complete that full revolution, right? And so that's 2 pi divided by 5, which is 1.3 radians per second, and it's going anti-clockwise, as you can see on the diagram. Part B, we want to show that the acceleration of the mass is given by a equals 4 pi squared r on t squared, where r is the radius and t is the period of motion. Here, all we need to do is just combine these two formulas here. So we're going to combine this a equals v squared on r, that's our centripetal acceleration, and v equals to 2 pi r on t. And we can then substitute 2 pi r on t for v in our centripetal acceleration equation. Simplify the algebra and you should get 4 pi squared r on t squared as required. And then we want to find the centripetal acceleration experienced by the mass. We can simply now just plug that into the formula we derived in part B. R is going to be 4 and the period is going to be 5. And so the acceleration is 6.3 meters per second squared towards the center. D. Explain what would happen to the mass if the angular velocity of the mass is doubled. Now, we know that the angular velocity is related to the period by this equation, w equals 2 pi on t, and notice that 2 pi is a constant. So if the angular velocity is doubled, in other words, the mass is swinging around faster, then obviously the period is going to be halved, right? Because they have an inverse relationship. If we spin the mass faster, the time it takes for it to go one revolution is going to be less. And so the previous period was 5 seconds, so the new period is going to be 2.5 seconds. Then the new acceleration is going to be, just subbing that into our formula we derived in part B, is going to be 25.27 meters per second squared, and thus the force, or I guess the tension, is going to be 197 newtons, right? And we've said that the string can withstand a maximum tension of 100 newtons, so the string will break. String breaks. Alright, moving on to question 24. So, a student is tracking a low Earth orbit satellite that orbits Earth every 120 minutes. Calculate the orbital velocity of this satellite. Now, the orbital velocity is given by 2 pi r on t, but we don't know its radius of orbit yet. Luckily, we can find that out by using Kepler's third law. So r cubed on t squared equals to gm on 4 pi squared. Rearrange that to solve for r, which is going to be the cube root of gmt squared over 4 pi squared. We can substitute all those values in. The value of mass, the mass of the Earth, you can find on your formula sheet. And you should get 8.07 times 10 to the 6 meters. That's its orbital radius. Then we can substitute that in to find the orbital velocity, and you should get 7,042 meters per second. Part B says, the same satellite needs to be moved 36,000 kilometers above the Earth's surface, and calculate the work that must be done against gravity if the satellite has a mass of 800 kilograms. So first we have to note that this 36,000 kilometers is not the final radius of its orbit, because we also have to account for the radius of the Earth. And so the actual RF, the final radius is going to be this value plus the radius of the Earth, which is going to be 4.24 times 10 to the 7 meters. Now to calculate the work is simply just changing energy, changing gravitational potential energy, which is the final potential energy minus the initial potential energy, noting our formula for gravitational potential energy here, and then we can just substitute on our values. Notice that our final radius is the value we calculated above here, and that the initial radius is exactly what we calculated above here. And so you should get 3.21 times 10 to the 10 joules. Alright, question 25. This is testing your working scientifically skills. We have an investigation to investigate the gravitational attraction force between two objects by varying the distance between the objects. And it is known that one of the objects has a mass of 45 kilograms. And here we have a graph of the experiment below. So first of all, we should fill in this table here by simply just reading it off from the graph. And so these are the values in the table here. And we can calculate this 1 on r squared by taking each value here and just taking the square of the reciprocal. Okay, so those are the values. And then we have to plot a graph of f on f against 1 on r squared. And so if you graph these values here, you should get something like this. Now, I've forgotten to put a title for my graph here, so I'll just add that in quickly. So maybe I'll just say relationship between the force of gravity, Fg, and 1 on r squared. Okay. I've plotted these values, I've labeled my x and y axis, I have a scale, I've labeled the axes, I've labeled the units, and also don't forget these the orders of magnitude. And that's my line of best fit over there. Okay, so part B, we need to use your graph to calculate the mass of the other object. Now note that the formula for gravity is F equals to gmm on r squared. We can just rewrite this as gmm times 1 on r squared, because these two, this f and this 1 on r squared, f is the dependent variable on the y-axis here, 1 on r squared is the independent variable on this x-axis here. And so it's following the sort of linear relationship like y equals mx, right, where m is the gradient. And so we know the gradient of the graph is equal to gmm. So to find the mass of the other object, there's two masses here, so we're just going to solve for the other one of the masses. That's going to be the gradient over gm, which is the gradient over 6.67 times 10 to the minus 11 times 45, which is one of the masses that we already knew. And depending on what your value for the gradient is, you're going to get a different mass, so I've just left that blank for now. Okay, so the next question is another graphical interpretation question. And we have this strobe light here, and that's showing the path of some particular projectile on Earth. The same projectile is fired on the surface of a planet with a lower acceleration due to gravity than the Earth. Projectile has the same initial speed and angle of projection. The same strobe light is used to film the projectile, and we want to draw the trajectory of the projectile on the surface of the planet for the first 0.4 seconds on the diagram above. Alright, so you notice that if the gravitational acceleration on that planet is lower, that means the force of gravity is going to be lower, and thus it won't be, I guess, as hindered by gravity, and so it's going to be able to fly further, it's going to be able to fly higher, and so it's going to take a sort of this trajectory like so, right? Notice that it still starts at 0, 0 because that's where it's launched from, but at every other point along its flight, it's going to be higher than the one on Earth, so it's going to take something like this. Alright, the next question is dealing with the similarities and differences between the Earth and the Moon and projectile motion. So, account for the similarities and differences between the motion of the projectile on Earth and an identical projectile launched on the surface of the Moon. Your analysis should include both qualitative and quantitative information. You may assume that the mass of the Moon is 7.35 times 10 to the 22 kilograms, and the radius of the moon is 1.74 times 10 to the 6 meters. And now the reason they've given us all this information is because we can use that information to find out the gravitational acceleration of the moon, which is given by the formula gm on r squared, noting that this m is the mass of the moon, this r is the radius of the moon, and we calculate that to be around 1.619 meters per second squared. And so we can now find the horizontal range of the we can now find the max height that the projectile reaches using our formula v squared equals u squared plus 2as, noting that at the max height the vertical velocity is equal to 0, and we can substitute all our other values in, and you get that the max height is going to be 272.35 meters, which is significantly higher than whatever max height we had here, which is not even 50 meters. Right, yes. Now for the similarities and differences between the path, well, because it's undergoing projectile motion, no matter what, it's going to follow a parabolic path, okay, which is a path like so, and we know that in both cases, near the surface of the moon and near the surface of the earth, the gravitational acceleration is approximately constant, okay. Now for the differences, obviously the time of flight is going to be different, the max height we just calculated is going to be different, and also the max range is going to be different. So essentially, the projectile is going to have just a much bigger trajectory in general. Okay, for questions 27, again dealing with orbits around satellites. So we have a spacecraft which is going to be placed into geostationary orbit around the Earth at point B, and we're going to assume no air resistance. So calculate the orbital speed of the spacecraft when it is in a geostationary orbit at point B. Now, similar to the question we did a few questions before, first we use Kepler's third law to find the orbital radius of the projectile when it's at a geostationary orbit, keeping in mind that the period of a geostationary orbit is just the amount of seconds in a day because it is geostationary. Working that out, we get that the orbital radius is 4.229 times 10 to the 7 meters. Then we can substitute that into our formula for the orbital speed, 2 pi r on t, and we should get 3.08 times 10 to the 3 meters per second. Now, part B tells us to calculate the change in gravitational potential energy of the spacecraft as it moves from point A to B. And so again, we just want to take the final potential energy minus the initial potential energy using this formula here. And we know that the final radius is, we calculate that above, which is approximately 4.23 times 10 to the 7. The initial radius is given on the diagram, 5.5 times 10 to the 7. Substitute in all those values and you should get that the change in gravitational potential energy is minus 2.1 times 10 to the 9 joules. Notice we're actually losing gravitational potential energy here because we're moving towards the Earth. Now, part C says, explain what happens to the total energy of the spacecraft as it moves from point A to point B. Now, due to the law of conservation of energy, the total energy is going to actually remain constant, right? But we want to explain why that happens, and that's because even though it's losing gravitational potential energy, it's actually gaining some kinetic energy. And in essence, the gravitational potential energy that is lost is converted into kinetic energy, and that's why at this geostationary orbit, it's going to have a higher orbital velocity than at this orbit right here, okay? So energy is just transformed from one form to another. Okay. The next part of the question says, after a while in geostationary orbit, the spacecraft turned on its thrusters momentarily to reduce its speed to 2.5 times 10 to the 3 meters per second. It then begins its descent to the surface as shown in the diagram below. Calculate the speed of the spacecraft just before it hits the surface at point C. Now, considering the path from B, so after the thrusters have been applied, and so when it's traveling at 2.5 times 10 to the 3 meters per second. So when we're considering this path here, in this path energy is still conserved because the thrusters are no longer acting. So energy is conserved along this path here, and so the final energy is equal to the initial energy. But energy is made up of two types, the potential energy and the kinetic energy. So UF plus KF equals to UI plus KI. Then we can rearrange to solve for the final kinetic energy, because we want to calculate the final speed of the spacecraft, and so that's going to help us there. That's equal to K initial plus U initial minus U final. Then we can use our formulas for kinetic and potential energy as shown. And I haven't done all the substitutions here, but you should be able to get all the values from the question. So for example, the initial speed is 2.5 times 10 to the 3 meters per second, and we know GMM from the previous part. All in all, when you substitute all the values in, you should get that the final velocity is equal to 1.1 times 10 to the 4 meters per second. Alright, we're almost at the end now. And now we're studying black holes. So there's a concept called the Schwarzschild radius, which is defined as the radius of the event horizon where gravity is powerful enough such that the velocity required for an object to escape exceeds the speed of light. We want to derive an expression for the Schwarzschild radius r of a non-rotating black hole m and physical constants. Assume a point source of gravity at the center of the black hole. So given that the question is sort of talking about the velocity required for an object to escape, we know it's probably going to be talking about escape velocity, right? So let's just recall how we derive an expression for escape velocity. Now, in any scenario, energy is always conserved. And so the initial energy of the system is always equal to the final energy of the system. Now, if you consider an object trying to escape the pull of the black hole, well, it's going to, or I guess in a simpler case, if you want to consider a rocket trying to leave the surface of a planet, it's trying to leave the surface of the planet, it's going to start off with some initial kinetic energy that's given by this half mv squared term here, and it's also going to have some initial gravitational potential energy equals to minus gmm on r. Now, if it travels with a certain amount of escape velocity, VE, then its final energy is going to be 0 because it's going to completely escape the pull of, it's going to completely escape the gravitational pull of the planet, or in this case the black hole, and thus it's going to have no gravitational potential energy at all, and it's also going to use up all of its kinetic energy. So its energy at the point infinity is going to be 0, but we know that has to also equal the initial energy because of the law of conservation of energy, and so we get the equation half mv squared minus gmm on r equals to 0. Move this to the other side, rearrange, use algebra, and we get that the escape velocity is equal to the square root of 2gm on r. So that's a formula for the escape velocity. Now, if we consider this special case where we're talking about black holes and the speed of light, we know that if you imagine, for example, a particle of light here, and it's trying to escape the black hole, we know that light always travels at the speed of light. Yes, that's pretty obvious. Light travels at the speed of light, which we denote in physics using the letter c. So at the event horizon, the escape velocity is equal to c, right? Because this is, because past that, the escape velocity is going to be greater than c, but that's not physically possible. So at the event horizon, the escape velocity is equal to c. So that means that c equals to root 2gm on r, and we can rearrange that expression to find that r equals to 2gm on c squared. Alright, going on to the second last question here, we have another banked tract, and in fact this is where we prove the formula that v squared equals to rg tan theta. So essentially, we have to show that the speed of a racer around a curve will be higher when they lean in compared to where they are upright. Include relevant free body diagrams in your answer. Now, I couldn't find a way, I'm not very good at drawing, so I couldn't find a way to accurately depict this scenario, but I have a mathematically equivalent scenario here, and that's where we're just considering say the rider is on a banked track, right? The rider leaning in at an angle and the rider riding on the banked track, which is at an angle, that's like mathematically the same thing. It's just that the bank is just doing the leaning, right? So in this scenario, what do we find here? Well, the biker is leaning in at an angle of theta, and we can use some trigonometry to determine that this angle up here is also equal to theta, and I should label what these arrows here. So obviously, yeah, so right here we have this normal force here, and the normal force is going to have some component that's going in the vertical direction, right? Now, since the racer or the bike rider or whatever, they're not accelerating up or down, right? They're just staying on level ground. And so the component of the normal force that's acting in this y-axis vertical direction here has to perfectly balance the weight force of the rider here. And that's why we have this arrow here, mg. That's the component of the normal force. We know that in circular motion, the rider is also going to have a component of centripetal acceleration that's going towards the center of the track there. And so that's our free body diagram for the rider. We can then use some simple trigonometry. We get that tan theta is equal to Fc on mg. Fc is our centripetal force. So the centripetal force is equal to mg tan theta. We know that the formula for centripetal force is mv squared on r. And from there we can cancel these two m's and then move the r to the other side. And then we take the square root on both sides. So we get that v equals to root rg on tan theta, or alternatively v squared equals to rg tan theta. Now we want to explain why the speed of the racer will be high when they lean in, and that's because the higher angle you have here, that is, the more you lean in, the higher your angle here is, right? And the higher your theta is, the higher your tan theta is, because tan theta is an increasing function, and that would in turn lead to a higher velocity. And so you really do want to be leaning in when you are racing around a curve. All right, the last question is a very tricky question, but essentially what we have here is that we have a dart. We have a dart that is aimed at a monkey hanging on a tree at an initial height of ht above the ground. At the same time that the dart is released from the person's hand, the monkey lets go of the branch and drops to the ground. All right, so the dart is launched and then the monkey starts falling down. Assuming that the dart has enough initial velocity to actually reach the monkey, mathematically prove that the dart will always hit the monkey. Alright, so first we should define some variables. So I'm going to let m equals the height of the monkey at some point t. So actually m is a function of t. And likewise, I'm going to let d equal to the height of the dart at any point t, right? And I'm assuming that the height, so this is level ground, so this is the height is equal to 0, right? So let's find an expression for m, height of the monkey, in terms of t. So we know from our Suvat equations, s equals to ut plus half at squared. And so we can apply that here, m equals to ut minus half gt squared. But it's also got this initial height of ht, which we also have to factor in. Right. Now, because the initial vertical velocity, this should be, I guess, uy. The initial vertical velocity of the monkey is 0, and so this just simplifies to ht minus half gt squared. Similarly, for the height of the dart at time t, it's going to be uyt minus half gt squared, but we know that the initial vertical velocity is simply equal to v sine theta t minus half gt squared. And so those are the two expressions we want to keep in mind. Also, we want to calculate the time at which the dart will theoretically hit the monkey. And we can first consider what times will the x displacements be equal, okay? What time will the x displacement be equal? Well, the x displacement of the monkey is not changing because it's just falling straight down. So the x displacements will be equal when this dart travels this distance of x. Now we know that x is equal to its initial horizontal velocity times the time it takes to reach that place, and so the time it takes for the horizontal displacements to match up is going to be x on v cos theta, where v cos theta is the initial horizontal velocity of the dart. Now, we know that when t equals x on v cos theta, the horizontal displacements of the dart and the monkey will be the same. But now what we need to check is that the vertical displacements are also the same, because if the horizontal and vertical displacements are the same, that means the dart has hit the monkey. That means they're in the same position, the dart has hit the monkey. So, substituting that value of t into our expression for d, the height of the dart, we get v sin theta times x on v cos theta minus half gt squared. That simplifies to x tan theta minus half gt squared. But notice that from the diagram, tan theta is opposite on adjacent, right? Which is ht on x. That's just looking at this diagram right here. And so we can substitute ht on x for tan theta into this expression here. And we get that d equals to, well, the x and the divided by x is going to cancel out. So we just get ht minus half gt squared. But that's exactly the expression for the height of the monkey. So we get that the height of the dart equals the height of the monkey at time t equals to x on v cos theta. Thus, at t equals to x on v cos theta, the horizontal and vertical positions are the same, and therefore the dart will always hit the monkey. Okay, and that's the end of the solutions for the Module 5 topic test.